Thanks, Drew, for the intro, and thanks everyone for coming here. So many of you, in fact, I really appreciate it. It's interesting you mentioned the restricted Boltzmann machines. I don't even know how many people. I'm kind of curious. How many people know what a restricted Boltzmann machine is? Just raise your hand. Okay, this is actually more than I expected. We have an ML PhD program. Okay. No, I know, but I don't even know if that I would teach it now because it's barely used anymore. They have a vested interest in RBMs. I have an online course, some of you might know, on deep learning and neural nets, and I have a whole section on this. And there aren't that many sections online on RBM. So if they come back, I think I might be even more famous. I think this is key for me to increase my profile. So anyone here, if you want to make RBMs work like really well on some important problem, then please go for it. I'll support you, potentially even financially. All right, but what I'll talk about today is my recent interest in a problem of few-shot learning, and particularly an approach that has become popular in the past, year or two, based on an idea called meta-learning. This is a talk that's actually not entirely focused on my own work, but I thought what I would do is kind of try to present an overview of this topic, including the work of many other great people, and maybe give you a sense also of what might be interesting challenges and opportunities for research that many of the young researchers here might want to engage in and investigate moving forward. So in terms of my trajectory, how I got to this particular problem was, well, first of all, just noticing that this amazing, great success we've had with deep learning approaches to many problems related to AI, all sort of working on the assumption that we have a lot of data available for these problems. And if we really truly believe in this trajectory that we're trying to make progress on towards AI that can solve any problems, the assumption that we'll actually be collecting, hundreds of thousands or millions of labeled examples for every individual AI problem that we'd like to solve is probably unrealistic. And just as unrealistic it was when we were talking about expert systems, and we would think that for any given problem we could just dump all the expert knowledge in a computer that would allow it to have the intelligence that we'd expect. And also, scientifically, it's quite interesting. Why is it that we as humans learn certain things very quickly from very few examples or exercises? If you're at school, it's essentially like a training data for humans. We can learn things very quickly from few examples, whereas our machines are kind of this, I make the comparison of a really, really hard-working student, but that's like really, really dumb and slow. It's just like work his ass off through like millions and millions of exercises, and eventually we'll get it. That's not how we operate. That's not how smart we are. So there's this scientific question here, which is, why is that? Why are we not there yet? And in previous years in my research, I've looked at one sort of high-level idea, which is, okay, well, let's try for any given problem to leverage data from other sources that aren't labeled data for that specific problem. And early in my career as a PhD student, I looked at using unlabeled data and doing unsupervised learning, using data that comes with multiple modalities. If you have images and text, then the text might serve as some sort of weak label for the image. But what I'll be talking about today is more in what I would call this multi-domain data. So the idea of let's try to do transfer learning in some way from problems where we have some data to problems where we don't have data. The one setup to keep in mind for most of this talk really is that the problem I want to address is one where the training set, the train that I'm given, is one which is maybe a 5-class classification problem, and I have very few examples for each. Maybe one labeled example, maybe 5 labeled examples. So in this case, I have 5 classes, Sundays, this thing, a dog, a lion, some bulls, and then I have a test set that I need a way of producing from this very small training set, the model that will generalize well to these images in the test set of this lion here and this bull. Okay, so that's the problem that we're trying to address. We want to solve problems of this form. So as I mentioned, people are actually quite good at it. This is an example that Josh Tenenbaum often gives. If I show you, if the first time you saw a segue like this, and then you were given all of these different images and were asked which ones are in the same category, I think a lot of people would more or less get the right answer. In particular, in this case, I identified this as the other segue. And also, machines are getting much better at it, perhaps not in the setting of supernatural images. But for instance, there's this paper, again, from Josh Tenenbaum's lab, where they used a form of meta learning, really, to get human-level performance on recognizing characters in various alphabets. Okay? So ultimately, so this corresponds to progress. It seems to suggest that we might start having tools that allows us to significantly progress. What I'm after in terms of, there's one sort of scientific mission, which is to close this gap between humans and machines. There's also a very sort of practical consideration, which is it'd be nice if we had, as users, a very simple way of defining classifiers and predictors, where we could just provide a few labels and then we'd get a pretty accurate classifier. One example of what this might look like that I like to give is from this website, Teachable Machine, which is this sort of web experiment that Google has come up with, where what I'll show you is just me having fun with my kids defining a training image classifier in 3 classes, the green and the purple, the orange class, where the green is going to be, actually, let's just start it up, but the green is going to be someone smiling, and the purple is going to be someone yawning, and the orange class is going to be someone being scared. So what I do, I collect data, where when I'm doing something with my webcam, I'm capturing the examples for each class by pressing the button. And then when you see the colors changing, that's the prediction of the classifier. So you can see once it has data about me, it's doing pretty well. Seeing my action skills in display here. But then, of course, if you go further out in the input distribution, I ask my daughter, the classifier is totally broken. It just doesn't work at all because it has only like 10 examples for each class. But then if she starts collecting some examples for herself, so smiling, yawning, and then being scared, then it sort of, after that, gets it. And ideally, what you'd want is systems where you can do this maybe for a few people, a few situations, a few contexts. And then it would be able to actually generalize well outside of that distribution. So say if I ask her sister to come along, who's a bit less shy, it sort of, in our case, it sort of works. It gets yawning and it gets, being scared. And this is sort of an example of the kind of generalization we'd like to be achieving. And granted here, my daughters, so they're supposed to look alike, assuming they share some of my genes, which I hope that they do. Now, obviously, this is a pretty hard problem. It took us a while to make that demo work. We took a bunch of different visual classes we might want to define. A bunch of them just were not working. So for natural images, just that fairly restricted setting is actually already quite challenging. But we could see that if we had a system like this, then if we think of making, one thing that deep learning has allowed is making the use of, say, computer vision methods much more robust, more easily usable by many people, including people in industry. And that's why there's been all this commercial interest. If we could even reduce the barrier in terms of not even having to collect tons of examples for any given classification problem, I think this could have a really big impact also just in industry. So those are these dual motivations. Scientifically speaking, I think there's something to learn about ourselves, about intelligence, and also this would really be practical. All right, so really the problem that we'll be looking at is we're going to try to address directly this problem of few-shot learning. So what I mean by that really is a problem where we need to, from a small training set of input and label pairs, where the number, so L, this number of examples is very small, what we want is a learning algorithm that will be able to produce, say, the parameters of a predictor or a model M that will generalize well to new examples that weren't in this training set. And here we're really focusing, the constraint we're putting on the setting is that this training set will be small. Okay, and that's the setting in which we're interested in its performance of this learning algorithm. And one approach that has become quite popular in the past 1 or 2 years is instead of sort of using all of our knowledge about how we might be doing this, say, or what are properties, say, of images that might be useful for having this strong generalization from few examples, instead, let's just try to learn that learning algorithm. Let's just treat the learning algorithm A that takes a set and produces parameters for a model. Let's make that something that we can train and that we'll train on examples of such problems. And so for that reason, we call it either learning to learn, or we more often call it the approach of meta-learning. Okay, and that's what I'll talk about. Now, the problem of few-shot learning itself is definitely not new. Just in general, doing transfer learning is a problem that people have looked at and is a concept that has been quite useful. There's these well-known results where if you train a model on ImageNet, it's been shown to transfer really well to different image classification problems, and in fact even surpass the hand-engineered features that had been designed in the computer vision community for a long time. And so here in few-shot learning, we're still going to rely on this idea of doing transfer learning on new data sets. But we're in a sense trying to transfer not just the features, but the whole process of going from a training set to a predictor that I can apply. Okay. And again, few-shot learning also in the context of, say, like one-shot learning. There's been a bunch of papers a bit more than 10 years ago where people were looking at that and making some progress. And a lot of that progress was, again, based on this idea of designing features largely. And so here, a lot at the core of deep learning is just this idea that let's try whenever we can to end-to-end train a system on data. That's really one of the key reasons why this has been working pretty well, this approach of deep learning. When in a sense, in meta-learning, we're going one step beyond that, and we say, let's end-to-end the learning algorithm. We have pretty good tools now to create computing programs that we can backpropagate through. Can we leverage that technology, but now to learn a learning algorithm? All right, so let's start to put some notation around this problem. So if we're going to talk about meta-learning, we should talk about just learning. So a learning algorithm, what is that? That's really an algorithm whose input is a training set of input and target pairs. And then its output is either a model or, let's say, the parameters of some model, which I'll sometimes call the learner. And a good learning algorithm is one that, for a given training set, produces a model that has good performance on a test set, from sort of a distribution of interest. That's effectively like a very basic definition for a learning algorithm. So then what should be a meta-learning algorithm? Well, it's a learning algorithm itself. But in this setting, the input is going to be a training set, but we're going to call that a meta-training set in the sense that it's actually going to contain, it's going to be a training set of data sets, where each data set is a split of a training set and its corresponding test set. And we have a bunch of these examples. So these training test set pairs, and we'll often call those episodes, will be the examples on which our meta-learning algorithm will be running and will be training a learning algorithm. So a good meta-learning algorithm would have parameters, but these parameters are the parameters of the learning algorithm. That is an algorithm A that takes a training set and produces the parameters of a model for that corresponding problem. And then a good meta-learning algorithm would be one where its performance is good on new episodes, so on new training and test set splits for other problems. Okay? So maybe a visual illustration of that will be more useful. But before I go there, this notion of measuring a generalization of a meta-learning algorithm, I think, is quite important. So small tangent, there's other sort of problems that some people might be tempted to call meta-learning problems. One of that might be doing what's called architecture search, where you're taking a neural net and you're optimizing the number of layers and the connectivity in that network. My claim is that if you don't take a procedure, a meta-learning procedure, and you don't evaluate it on new problems, then it's not really meta-learning. It's more like optimization. So if you're working on CFAR10 and you're optimizing the architecture for CFAR10 to get a good performance for the test set of CFAR10, that's hyperparameter optimization, or it's closer to optimization than it is close to learning. Learning would be like training that procedure that optimizes the hyperparameters and the architecture of a neural net, and training that on, say, CFAR10, and then showing that it actually works well also on some other image classification problem or some other machine learning problem. And that, to me, is meta-learning. There needs to be this notion of generalization to new problems. I saw a hand, yes?
What is the relation between the meta-training and the meta-test? Is there an assumption they're coming from similar distribution, or could they be from a totally different distribution?
Yeah, so the question is about what's the relationship between these problems in meta-training and meta-tests, and I think this will get clearer as I move forward. But that's actually a problem in itself, and that's something where I think also right now STEAM needs to iterate on as to how do we define that problem. But so visually what this problem will look like, as I mentioned, what we want is essentially a learning algorithm that generalizes well. You didn't open your chips before. Let's all wait for Dhruv opening his chips. There you go. All right, so in meta-learning, what we want to do is, as I said, we want to tackle this particular problem. We have a small training set, and we want it to produce parameters for its corresponding test set. So in meta-learning, as I mentioned, we will have these problems will be in our essentially meta-test set, and then we'll assume that we have a meta-training set of other episodes, where this episode is kind of this grayed out capsule here where you have a training and test set split. And in particular, in the way we usually set up the problem is that we make sure that in the meta-training set, we have images of classes that are different from the classes that are in the meta-test set. And that's the extent to which we're measuring generalization. So here we're going to ask for, in some sense, an extrapolation to classes that it's never seen before. So in particular, these examples are coming from what's called the mini-ImageNet benchmark. Which is essentially a subset of ImageNet where we've taken 64 classes to construct the episodes for meta-training. And then we have another 20 set of 20 classes that are used for the images in the meta-test set. Okay? And so here you can see that you have piano as one of the classes in the episodes of the meta-training set, but we'll not find any pianos in the meta-test set, in none of the images. Okay? And so in meta-learning, really what we're trying to do is to iterate when we're meta-training. We're iterating over this meta-training set. And so we go over the first episode. And then we're going to have our meta-learner that's going to take as input. And the meta-learner is where the parameters of our meta-learning approach is sitting. Those parameters are we're learning. We're going to feed in the training set into the meta-learner. And conceptually, that meta-learner is going to produce a learner through outputting parameters for it, or it's going to produce a model that I can now apply, that I can take as input a test example, a test input, and make a prediction for its label. And now what I do to set up my meta-learning training objective is that I'm going to define a loss between what is the learner's outputs on the test set examples of that episode, and I'm going to backpropagate backwards through these arrows. I'm going to find a way of adjusting the parameters that are in the meta-learner here to optimize the loss. So here we're trying to get as close as we can of the problem of generalization to some extent. We're trying to optimize a meta-learner that produces models, M, that actually generalize to test examples that were not fed as input to the learning algorithm. Okay? And then maybe if we do gradient descent, which is usually what we do an update on the meta-learner's parameter, and then we move to the next episode. The meta-learner gets a different training set, produces a different model, look at the loss on the corresponding test set examples, and then again backpropagate into the meta-learner. Okay? Are there any questions about this setup? I'm sure there are. Anyone has the courage to ask these questions? Yes?
So your meta-learner is never taking the learner as input. It's always generating one, right?
Yes, the meta-learner is not explicitly, at least, taking a learner as input.
So it has no notion of definition for the problem at hand, or?
It does not have access to a definition of the learners, at least not in some sort of structured format. So we'll see a bunch of examples of meta-learners. There are some approaches to meta-learning right now that will now allow you to change what is the family of the model, say at meta-test time. It will just assume the meta-learner only produces parameters for a convnet with 4 layers. So approaches like mammal and approaches like that are sort of that nature. And I think right now I can't really think of any approach in meta-learning where the type of learner really drastically changes between, say, episodes. And I think, down the line, that's definitely something that we want to consider and investigate. But yeah, often they're making fairly strong assumptions about the nature of the learner, such as, what parameters it has. Yeah.
Given the parameters, the hyperparameters you just mentioned, is there a meta-val test? Meta-val?
There's a meta-validation set, yeah, with 16 other classes that are different from both meta-testing, meta-training. Yes, absolutely. Yeah.
So how you quantify the loss when you miscategorize something? Do they all belong?
Yeah, it's essentially a cross-entropy loss that we'll be using, and we will see that in a bit, but yeah. All right. So a quick note on some of the nomenclature you'll find in papers. So the notation I like to use is to talk about within an episode there being a split of a training set and a test set. And then we have this notion of meta-training set that we train the meta-learner on, and a meta-test set for generalization for meta-learning. It really establishes, it sort of follows this concept that here we were training a learning algorithm. It gets pretty hairy in both writing the paper or presenting it, as I found in my previous presentations. To have both training sets and meta-training sets, sometimes you get confused as to which one you're referring to. So you'll find some papers that will instead of talking about a training set in an episode, they'll say that's the support set, and that the test set is instead a query set. And then you can just use training and test set for these sets of episodes. It is definitely clearer, that notation. I don't find it as cool, so that's why I tend to avoid it. It's not the best reason, but and so I will try to stick with this notation. But be aware that you might read a paper in meta-learning, and they might, if they talk about the support set and the query set, they're referring to this split within each episode of the examples, the set of examples fed as input to the learning algorithm, and the query set is just the test examples on which you're evaluating the loss for that episode. All right, and so then if you have this procedure that takes a training set and then allows you to produce a model, if that model defines a distribution over what could be the label for a new test set input in my episode. So one way of writing it is that this model is effectively also conditioning on the training set. That's kind of what this whole procedure is. You can think of it as giving you a conditional distribution of the label of a new input given the full training set. Well, one thing we can do for the loss of n episode is to optimize the average negative log probability of those label assignments, the cross-entropy loss, as we often refer to it, for that episode, averaging over all test set examples in that episode. And now, depending on the choice of what the meta-learner is, and various approaches published so far, essentially, often what will really change is this. That is, we're going to do gradient descent on that objective, and then we'll just use various definitions of that conditional distribution effectively. And so what I'll do now for most of this presentation really is that I'll go over the various approaches that have been early on some of the most successful ones. And it also kind of span various approaches one might take for this problem. So I think there's sort of good things to know about if you want to dive into this literature moving forward. I'd like to think there being sort of two categories of approaches. One of them is, let's not throw out all the literature on machine learning algorithms. Let's instead take inspiration from how the actual sort of hand-designed machine learning algorithms, the structure that they take and how they function. But let's just introduce some parameters in them, and let's train those parameters with meta-learning. And so some take inspiration from what a KNN predictor or kernel machine might look like, and that's essentially matching networks. There's this relationship between assuming a Gaussian classifier in some learned latent space and training with prototypical networks, which is another approach I'll talk about. There's another one, which is, well, a lot of our training algorithms are essentially gradient descent based. Well, let's use gradient descent as the model for our meta-learner. I'll talk about that. Mammal is an example of that. And then there's the other approach, which is to say, you know what, maybe we're wrong about what a learning algorithm should look like. And maybe it should just be some black box generic neural network that we will be training to make these predictions, these conditional predictions where I have a new input, I have a training set, and there's some black box neural net that produces a softmax over the labels. I'm not going to talk about MAN so much, though it was one of the early examples of doing that. I'm instead going to cover Snail, which is more recent and up there in the state-of-the-art approaches. But let's first start with the first family, where we're taking inspiration from known learning algorithms. So one of the first ones that were proposed was the matching networks coming from DeepMind, from Aurel Vignal. And there, the idea is that we're going to assume that the label y is predicted essentially based on doing a linear combination of the labels that I have in my training set in my episode, where the weight is essentially a function of what is the input associated with that label that I'm weighting, and what is my test set input that I'm trying to make a prediction for. And so here the y's are essentially one-hot vectors. And so with these weights, if they sum to 1, then you're going to get a distribution essentially over the label of x hat, where x hat is in my episode. That's one of the test set inputs. And one way of doing this, one way of parameterizing this weight here, essentially this vote for xi voting for its actual label in the training set, is to do a softmax over some sort of comparison function between a representation of the test input, x hat, and some other representation of the training set input, xi. And they've looked at various architectures for representing both function j and f. So wait, that's g. I said j, didn't I? Sorry, French hiccup. So they've looked at, for instance, using different neural nets for both. They've looked at, and this is sort of this dotted line arrow here, where you could have the representation of the test input modulate how you process the full training set. Also defining an actual RNN that is going in some arbitrary order in both directions, all the inputs in the training set. And so, trying to make those two representations as expressive as they can, and actually finding that they can get better results by using some sort of bidirectional RNN on this set where you sort of order it in some arbitrary order. And so that's essentially just end-to-end learning a pattern matcher so that it is able to make the right prediction to a new label for a new example. Another approach that's one of my favorites because it's super simple. So it's a good first approach to consider for as a meta-learning approach. It's quite fast to train and quite simple. Is this approach called a prototypical network, where what we're trying to learn is per class, we're going to learn a prototype. And essentially, the way we're going to classify some test example x, I guess the previous notation that would be x hat, and here and here. But what we'll do is that we'll take my test input, we'll map it into some representation space, and then we will compare that with the prototype of each class using some negative distance function. Could be Euclidean, could be cosine. And then we'll just pass these negative distances or these similarities through a softmax. And that's how we get our distribution over the labels. And the prototype themselves, you can imagine various architectures for extracting a prototype for each class. Here they use something very simple, which is essentially you take, say, some convolutional neural net that maps to a vector space, and then you take the average per class of those vectors. So quite simple. So this is the notation here, where sk is essentially this set of all examples x, y, where the y is actually correspond to all examples in class K. And here, really, the parameters of the meta learner are essentially just the representation, because we fixed out that representation is used. So effectively, you're sort of end-to-end learning that representation such that if it's used in what is effectively something like a Gaussian classifier, where in a Gaussian classifier you would just take the average representation of all classes, and then you would essentially look at the likelihood under these means of each Gaussian of a test example, and you would use that to make a prediction. If you use, for this distance here, the squared Euclidean distance, then you recover essentially a Gaussian classifier on that representation. But you're learning it explicitly such that it works well for a Gaussian classifier. So that's in the sense that is effectively a form of meta-learning. So I've mentioned that, yeah, we get a Gaussian classifier effectively if we use the Euclidean squared. Also, if you use the Euclidean function, which often actually works surprisingly well, you can also show that the prototypes are effectively acting as the output weights of a neural net that is applied on the test example. So this, essentially the embedding function would be kind of like the first few layers of that model you apply on test examples, and then the prototypes are providing the output weights. And that's essentially because if you have the squared Euclidean distance, you can refactor that into a term that multiplies the representation with the prototypes, and then you have this constant term that's the bias. So you can kind of think of it also as producing the weights, but only the output weights of a neural net that you're applying on the test set of a given episode. And yes?
I guess you could do something like k-mean, you do k-meanoids if you start taking not the average of those representations, but the
right.
representation.
So yeah, so how you get a prototype, I think there's presumably some innovation that could be done there. Why have just one prototype per class? That's kind of a very simplifying assumption. Why use this average pooling? So you can think of it as, we're doing average pooling here, the level of classes. Could do other types of pooling, could do max pooling, could do other things. Yeah. And then the third approach that's sort of within this family, let's take inspiration from learning algorithms that exist, is to actually take some inspiration from gradient descent. So right now, one of the most successful learning algorithm is stochastic gradient descent. So we come up with some parameterization of our learner, of our model. And then, as you know, gradient descent, we just come up with, we initialize the parameters theta 0 of our model, and then we sort of apply this update rule several times where this is the loss as measured on a mini batch. And so this is the gradient of my current parameter values of that loss. And I go in the opposite direction of the gradient with some step size, move in that direction in my parameter space, and that gives me the new parameters. Okay. Well, that formula might be a good inspiration from what could be kind of like some sort of recurrent neural net that's actually iterated and unrolled in the space of parameters. And that was sort of our inspiration in this iClear paper with Sachin Ravi in 2017, where we kind of noticed the similarity between this and, for instance, an LSTM state. So if you're familiar with LSTMs, you have this cell state, which is updated by taking the current cell state and then possibly modulating that with a forget gate, and then adding a update to the cell state, the C tilde, which is modulated by an input gate. Okay, and the input gate, the forget gate, pretty much everything here is sort of produced by a form of a recurrent neural network. Now, if we make this cell state be the parameter vector for my model, say my convnet that I want to train to do image classification on some problem. So if CT becomes theta t, and let's say I just fixed FT to be 1, so no forget gate, and IT is just effectively going to be my learning rate, and then I impose the cell state update to be going in the negative direction of the gradient of the loss for my training data in my episode, with respect to my parameters, I essentially recover the same equation. Okay? And we're able to train LSTMs fine, very well, in fact. So that suggests that we should be able to backpropagate through a few iterations of gradient descent. So that was kind of the inspiration here, where we sort of effectively have a LSTM, which is why we called our method meta-LSTM. But there, the cell state was imposed to be the parameter space of some convnet. And the cell state update was imposed to be the negative gradient of the convnet parameters on the loss of the current mini batch. And then we use otherwise regular input and forget gates, which are effectively, we actually decided to learn a forget gate because it's kind of acting as a regularizer. So since it's multiplying by a term that might be smaller than 1, it is effectively shrinking the current parameter values a bit close to 0. And the input gate is effectively the learning rate, so to what extent you want to move fast. So it could potentially learn to both optimize and regularize, depending on what it does on the input and forget gate. So more visually, yeah, I think I've said all of that. Visually speaking, this is what it would look like. So for a given episode where I have a training set and a test set, I would start with some initial values of the parameters of my convnet. So all the convolutional filters, the fully connected layers. And then for the output weights, since there's no real transfer that can happen there, so for a given episode, if we have 5 classes, we sort of randomly order them and assign them integers from 1 to 5. So there's no real structure in the output weights that we can learn. So we just initialize those to be 0. Then we look, OK, for that initial value of the parameters, what's my loss on my first mini batch of inputs x and labels y? Since we're doing few shot learning, we actually use the full training set. Because in our experiments, we use at most 5 classes and 5 examples per class. So that's a very small mini batch already, essentially. And so for doing the forward pass with theta 0 on x and looking at the loss for y, that gives me a gradient on my loss. And now I feed that gradient to the MODEL learner, which is going to combine that with the current value of the parameters theta 0 to give me a new value of the parameters of my convnet theta 1. And then I look, OK, now with theta 1, what's the gradient for my second mini batch, which when we're free shot learning, that's just the training set, as I mentioned. And then I get a new gradient, which I combine with theta 1 to give me a new parameter value theta 2. And I sort of iterate that, unrolling my graph until I get a final value of the parameters theta t. And then I take theta t, and now I look what is the loss, but now on the inputs in the test set in my episodes. These examples that were not used in computing any of the gradients, were not used anywhere in this forward pass here. And then I look at what's the loss on those examples, and that's this C term here. And then what I do is I backpropagate through this whole recursive graph here, much like I would backpropagate through an RNN or LSTM. We actually do block some gradients. So the gradient that we get here is effectively a function of the parameters of my MODEL learner. So I have to do gradients of gradients, which is computationally expensive. And so it might take a lot of memory. So we find in practice that ignoring those gradients sometimes is fine. In this particular results that I'll be presenting, we were able to get good results. So we're blocking those gradients largely for compute efficiency reasons. And then we backpropagate into all the parameters of my MODEL learners. And those parameters, they are the parameters inside of the thing that's giving me my input gate and my forget gate. But they're also going to be the initial parameters. So where do I start my optimization? What is the initial value of my convnet before I do a few steps of gradient descent? And in fact, a lot of the transfer is going to happen from there. You can think of this train initial parameter vector as being essentially what's a parameter vector that's close to the solution across all the episodes. And then these few gradient steps for a given episode, it's just going to bring me close to what is the right solution for that episode. Okay? So a lot of transfer learning actually happens through that trained initialization. Another way of thinking of it is that we're end-to-end learning this pre-train followed by fine-tuning. In pre-training, you sort of do a bunch of training on some data, then you fix these parameters, and then you just do a bit of gradient descent step updates on a new data set that isn't necessarily the one you pre-trained on. Here, we're essentially end-to-end training both that. We're training initialization such that if I do a bit of fine-tuning, I'm going to get better results because it's trained end-to-end to do that well. Yes?
In computer vision, at least, there's a number of tricks that are studied about initialization. So even if you drop the pre-training perspective, just initializing CNNs or neural networks, whether you should look at fan in, fan out, and or should you have initializations that are close to 0. Did you find something consistent here across data sets that shed some light on
Yeah.
might be a good data set agnostic initialization?
Right. So I guess, yeah, the question is whether we've looked at whether what is recovered in terms of initialization reflects some of the sort of built-in knowledge from training these neural nets that we've discovered. Actually, that's a great question. We haven't looked at what it was learning in terms of the initialization. We did look at what the input gate and the forget gates were learning. It was not interpretable. It was really hard to make sense of, in fact. So it's not clear what it's learning. I know that one inspiration from this paper was a previous paper by David Duveneau and others at Harvard, where they did that. They backpropped through multiple steps of gradient descent, but they actually did it on large data sets. And here we're going to backprop through like 12 steps of gradient descent. So really doing a few steps of gradient descent on a given episode, largely for compute reasons, but also because we're in a few-shot learning setting, we suspect that we shouldn't be doing too many steps of gradient descent. Otherwise, we risk overfitting. But this work that David Duveneau did was meant to try to see what kind of knowledge would be extracted from doing that. They didn't look at, they might have looked at properties of the initialization, I don't remember. But they did look at the types of learning rates that were learned. And they find these interesting things where they saw that unintuitively, what seemed to be optimal was to train I think it was training the top layer first a lot. And then, now I regret because I'm not sure if what I'm saying is the right thing. Maybe I can just, because I know I have the slide somewhere.
It's fine.
Yeah. So, yeah, the last layer, the learning rate would jump up early on, and then would just go back down. This is just what the learning rate is that was trained in an end-to-end way. And then later on, it would instead crank up the learning rate of the first layer. Now, this almost certainly not globally optimal, but it was kind of interesting that this is not common wisdom necessarily, because the fear when you're training a deep neural net is that initially the features are random, so the output weights can't really learn anything meaningful until the features have been learned. But so to see this, what's kind of surprising. OK. Yes?
Does the order in which you present the training, meta-training testing sets, does that matter here or in general in meta learning?
So the way we do it is, well, for the mini batches, in this approach in particular, since we're using the full gradient on the mini batch, then it's order agnostic because we take an average over those. The matching network, the approach where they would use an RNN, a bidirectional RNN, over the set of inputs, it's got to be dependent. So I'm sure if you shifted for a given episode, you take the training set and you try different orders, you're going to get different predictions. And my guess, in fact, is that if you want to slightly improve your results, at meta test time, you take an episode, you try with multiple random orderings of the input examples, and you just average the predictions you're getting. I wouldn't be surprised that this is like a valuable form of sort of variance reduction that would give you some results, some better results. In this setting, because we're using the full batch gradient, when we're computing that gradient here, that goes into the MODEL-AGNOSTIC LSTM, then it's actually agnostic. It's not dependent on order.
What about the episodes themselves?
Mm.
What about, because it's an LSTM, what about if you show different training sets earlier on?
Right. Yeah. So the order of the episodes themselves. I don't know that it is more dependent on order than, say, just regular stochastic gradient descent is dependent on the orders of mini batches. I don't have a reason to think of it as being more or less dependent. It might be, but we did find that what's interesting is that if you take a regular approach to learning a representation, which would be to train on all of the data that is present in all the episodes, and then you use that to initialize, say, this approach or prototypical network or something like that, we do tend to find that we get better results. This is more recent, like in the past few months, there's been a few results suggesting that, which suggests that there are properties about this optimization problem set up this way that are maybe challenging and are not well understood yet. So that would be the only reason why I would think that there might be something more clever that one wants to do in terms of how to create these episodes for training. Yeah, it's a great question. OK. Oh, do I? OK. I'm going to ignore that. I I'll go quickly over MAML. So MAML came out a few months after our paper at iClear. And there, what's interesting is that what they did effectively is that they removed the LSTM part, so the input and forget gate. So essentially trying to learn a model that produces the regularizer and the gradient descent, the learning rate at each time step. Just remove that. Assume you're doing constant learning rate updates, but still learn the initialization, and it would get as good results and often better. It even seems to be more stable, and which is interesting because you would think that this is pretty small capacity meta learner, but there's even theoretical results where Chelsea Finn, this is from Chelsea Finn from Berkeley, where she could also show that this restricted form of a meta learner is actually a universal approximator under some assumptions, which again is sort of suggesting that you actually there's an inductive bias, but it's not one that removes any potential for universal approximation. And so if you were to use a method that's gradient based like this, I would not use the meta learner LSTM, which it turns out like a bit overly complicated. It turns out that entirely using the full form of constant gradient descent, constant learning rate gradient descent was sufficient to do meta learning and learn a good initialization. And then the other approach that I mentioned is to actually say, let's ignore all of these machine learning algorithms that exist. Let's not take inspiration from that, really. And let's just apply some sort of black box sequential neural network to actually effectively train it such that it can only learn a learning algorithm. So one way of doing that is that you set up a sequential prediction problem where you feed in as the first steps of the sequence the input and the corresponding label in the training set of the episode. And then only at the very end, you provide the input of a test set example in that episode. And of course, you don't provide the label, because otherwise it could cheat and just copy the label at the output. So you provide like nothing here. Essentially, there's a bunch of zeros. But you have this sequential neural net that is able then to make a prediction of what is this label that's missing here. Okay? And then you use modules that we're familiar with that allows us to handle sequences of variable size. So in their case, what they used is dilated convolutions and using self-attention layers. So here you have convolutions, attention, convolution, and some more attention at the top. And without going into details, what they found is that you could train this very black box module to actually do surprisingly well in terms of making predictions for new problems and effectively learning some sort of learning algorithm. And so that's another approach. And it could be that we're going to design some other form of, some people have looked at using memory networks, previously LSTMs. This is right now kind of like the best results in that category of approaches. But who knows if the state of the art and how we make sequence to sequence predictions changes. This approach might eventually become, more successful. But so going to the results, these are the initial results we presented early on in 2017 on this mini ImageNet benchmark, which has kind of become the de facto benchmark that people use in few-shot learning. The way it works, it was actually originally proposed by Oriol Vignal in the matching network paper, but not all the details of how to reproduce that benchmark were provided. So we now later on sort of reproduce that challenge and that benchmark, and people can ask for it if they want to compare with our results. But essentially, it took just 100 classes from ImageNet, then split that 100 class into 64 for training, 16 for validation, 20 for testing. To generate episodes, you take, if you're in the meta training set, you take a random subset of, if you're doing 5 class, and that's all we'll do here, you take a random subset of 5 classes from these 64 classes. If you're doing one shot, then for each of these classes, you take just a single randomly selected image, and you put that image in the training set. And then in the test set of the episode, you take, I think it's 10, I forget the exact number, but a few more examples from that class from the same 5 classes that were selected in that episode. And then if you're doing a validation set episode, you're instead drawing the classes from these 16 validation classes and 20 testing if you're in meta testing. And so then the first thing that we want to see is whether we can do better than fairly simple baselines, which is essentially learner representation on all of data from all of the 64 training classes in this very simple way. We're just doing 64-way classification on mini batches drawn from these 64 classes, and then do something after on the episodes in the meta test set. You can either do fine-tuning, just assuming, OK, let's say we just do 5 steps of gradient descent from the initialization that was pre-trained. And that actually doesn't work really well in our experiments, which kind of suggests that end-to-end learning deinitialization in the context where it's used, where you're doing a few gradient descent steps after, is indeed valuable. It's really hard to sort of do pre-training separately in such a way that will work well if you do fine-tuning at meta test time. And the other approach is, of course, just use that representation. So scrapping the output layer, just use the top hidden layer, and then doing nearest neighbor matching or nearest neighbor prediction in the episode of the meta test set. That actually works, pretty well. But thanks to meta learning, we are able to edge out that performance from a little bit to a fair amount. These are the results for matching networks. FCE refers to using this sort of more complicated encoding of the test and the training set. We're using this bidirectional RNN. So they managed to get a bit better results with that. And our middle learner LSTM at that time was doing a bit better, in particular in the 5-shot setting. And then later on, more results were published using prototypical networks, mammal and snail. We have the results here. For me, the conclusion is more or less that all of these results are about around the same ballpark. There are certain design choices that are a bit different sometimes between these. I think prototypical networks might be a slightly bigger neural net than, say, in mammal. I know snail, they use like residual connections and they use like a pretty big neural net, whereas mammal was trying to use the same number of parameters as in matching networks and our work. So these are not entirely comparable. And right now we are working on trying to define a new benchmark where we don't have these issues that we can not compare with things in the past and also make the benchmarks more substantial than just 100 classes. But all these methods indeed seem to be able to edge out like what would have been the sort of learner representation and then use it in some other method after. So in terms of, I want to close with talking about challenges. The notion of how do we define these episodes, how do we define a distribution over training and test sets is here really arbitrary. We make a pretty strong assumption, which is that all the problems we'll be facing at meta test time are 5-class problems. And either they're going to be 1-shot or going to be 5-shot. And in fact, in our case, we train one model for 1-shot and one model for 5-shot. Designing methods that are actually robust to the number of ways and the number of shots in episodes, that's like the natural next step for this research. Because of course, in this little demo that I showed, the number of examples that I was collecting with my webcam, with my laptop camera, was kind of unknown a priori. I didn't even know myself how many I was going to provide. But also, to what extent, sort of measuring our ability to do generalization to new classes and getting a sense in which are we able to sort of go really beyond the support of the classes that we have at training time or meta training time should be something we need to study more. So as I mentioned, we are currently sort of working on a challenge where it would effectively be multiple data sets. So right now, we effectively took ImageNet and simulated many data sets from it. But in real life, we would have really different data sets. The data set you would meet and we would see at meta test time would be different from what you've seen before. So we're trying to create this benchmark where it would look something a bit closer to that. And finally, here we only studied supervised classification, but we could go beyond this. There are other settings that are interesting. So one of them is doing semi-supervised learning. So this is work we published at iClear this year, where in our episodes, we assume that now we don't only have a few labeled examples, we have potentially 10 times more unlabeled examples, where these examples belong to any one of the classes for this problem, but also, and these are the minuses here, we have some images that are not from any of the classes that we call distractors. And in that paper, meta learning for semi-supervised 3-shot classification, which I won't go over because I don't have enough time, we sort of extend prototypical networks to that setup, where effectively what we're doing is we're doing a two-step process where we're going from the training set. We're going to try to infer some soft labels for the unlabeled set and include these soft labels back into how we compute prototypes for each class, and then look at the performance of these prototypes, predicting the label in the test set of the episodes, and then back propagating through this whole sort of two-step process, and finding that we can do better than not end-to-end learning that process as well. We could do few-shot distribution estimation. This is a paper from DeepMind where what they did is that, imagine the problem where I give you a few examples from just one class of characters, and then I want a system that produces a generative model that can generate more examples that look like they come from that distribution. This is also a paper at iClear. And I have this ongoing AI On project, which is a project anyone can participate in. It's sort of an experiment in open research where anyone can come in and say, I want to help out, I want to participate. We have a GitHub, we have a Slack channel, and people come in, read the literature, and if they have time, they can try to contribute to our code base. Where here we're trying to apply some of these ideas of few-shot distribution, but for music generation, where the idea would be that an artist would come in and be like, I want to hear melodies that kind of sound like these. And then you would immediately get a generative model, and that might give you some artistic ideas for that artist to write, a new song. You can end-to-end learn a data augmentation network. This is work from Facebook, which I find really interesting, where they're using prototypical networks again here. But now the idea is that what we're going to train also is a model that takes in one of the training examples, concatenated with some noise, and which produces a new image, or at least a vector that fits in the input space. And then that's going to get the same label as the original image. And then if we concatenate that to the training set in the episode and feed this into a prototypical network, you want to train this generator to improve the performance of the prototypical network. So it might not actually generate images that look like images, but it's generating things that help in, say, defining the prototypes, and in such a way that you get better generalization. So I thought it was kind of a clever thing to do. You can do program induction, where the idea here is that in this paper from NIPS, you have these Carroll sample tasks where you're given an input of a program and what is the output, which is essentially a program that moves this little guy here that in this case is sort of moving down and putting a little circle wherever there's no brick wall. So this is actually this program here. But now assume that you're only observing the input and the corresponding output of that program. You would like to extract from many input-output pairs a model that can actually take a new input and produce the right output. Okay? The only thing that's programmed here is that we know the underlying function that created these targets come from some language, from an actual program. And so what they did there is that they showed you could use something that's somewhat similar to a prototypical network, where you would have a task encoder that would take all the input-output pairs, encode it in some space, do some pooling, and then use that to condition a output decoder that takes in an input and needs now to produce the correct output for a new input. So this paper might be worth looking at. I realize I'm going fast, but sort of out of time. And this is in the space of structured prediction. And there's this other problem that's interesting where you might want to do few-shot image segmentation, where here the user is providing you just a few key points with what is the positive class and what is just background. And now you want a neural net that takes in this annotation and the corresponding image, and then is able to condition on that another network that will take a new image and needs to produce the full segmentation for that same category. So in this case, you see that the white dots are around the dog. And so here, what you want is the network to learn, OK, then my representation of the task is that I should segment out the dogs in images. And so if you connect these two components, you can end-to-end learn the encoding of the task such that this network here that's applied on the new image is doing dog segmentation and not other types of segmentations. And I think ultimately, really where we want to go is this more like interactive setting. So I mentioned that the goal is to have someone provide examples, see the performance, correct by providing new examples, and so on. And that might lead us to think about how to do meta-active learning. So maybe you want the system to also suggest, can you label this? Because I'm not sure what you want for this. And right now, there's been some people looking at this, but not with a whole lot of success, I would say. So I think that's still sort of an open question. Can we learn an active learning policy, for instance? We did have some work published at NIPS where we were doing this in the context of recommendation, where for a given user, you would provide what is the items that they've engaged with and didn't engage with, and that would condition a model that would make prediction as to whether you would engage for a new item. But I think we've barely scratched the surface in this sort of interactive setting. All right, so those are the challenges that I encourage people to think about, sort of thinking about how we, and things that I think our community should think about, thinking about we define new benchmarks that are a bit more realistic. Going beyond supervised classification, I think there's tons of opportunities there, and also moving more closely to this interactive setting. And with that, thank you all.